Now, the astute viewer will have guessed or figured out that this whole domino game thing is really math in disguise. And you're right, the dominoes are really just vectors, and the operations that you're doing on the dominoes, including multiplying them by something and then adding them together, are precisely the vector operations that we've already learned: scalar vector multiplication and vector addition. And the name of the game, of the domino game, is basically figuring out what dominoes you can make from other dominoes. And I want to introduce a concept now, which is called a linear combination. And this is going to turn out to be a very key concept for us. So a linear combination of vectors is essentially multiplying each of them by a scalar, which could be 0, and then adding them up. And any vector that you can get in that way is a linear combination of the vectors that you started with. And if you think about it, you'll realize that's exactly the domino game. The whole name of the game in domino land is find a linear combination of the starter dominoes that is equal to the white domino that you're trying to get. And we will frequently talk in this class about all the vectors that you can get through linear combinations of another set. And that turns out to be a really key thing. Now, one of the things I want to do in this segment is sort of give you some intuition about how all these things play together. And in order to do that, I want to get a different sort of look at the domino game. So when you were playing the domino game, you weren't necessarily thinking you were doing math, but the perspective that I'm going to give you right now is going to seem more mathy. What we're going to do is we're going to plot the dominoes in a coordinate plane, okay, just like you learned how to do in middle school or whatever. Here is the first picture I'm going to show you, and you'll see I've got an X and Y axis here. And what I've done is I've taken our two starter dominoes, which in the yellow case, if you recall, were 1, 2, and 4, 4. I've written them here as vectors instead of dominoes, but it's the same thing, right? And I've just plotted each of those in our coordinate plane. So here's the vector 1, 2. Remember, a vector starts from the origin and goes to a particular point. This one goes to a point that is 1 unit over in the x-axis and 2 units up in the y-axis. And then I've got 4, 4 here, which goes 4 over and 4 up. And the other little faint yellow lines I have here that are sort of dotted are basically just showing the direction of each of our starter dominoes. And you'll realize that if you take the domino 1, 2, and you multiply it by any scalar, you will get some point on this line, right? In other words, that domino by itself allows you to get anywhere you need to get on this line. And similarly with 4, 4 allows you to get on this line, right? So when you see it from that perspective, you'll start to realize what the answer is to the question I asked, which is, hey, does every white domino have a solution? Are you always able to find one? You'll see that you are. Here's why. So let's take the domino 6, 8, which I believe was the first one I gave you. Really what we're asking is, hey, is there any way I can follow a vector in this direction and then follow a vector in this direction, because that's really what you're doing when you're adding vectors, right, is you're going in one direction and then in the other direction of the two vectors. Is there a way I can do that and land at the point 6, 8? And of course there is. We saw that with the domino game, and here's what the picture looks like. I was going to add 2 of the vectors in the 1, 2 direction, and then I was going to add it to 1 of the vectors in the 4, 4 direction. So you'll see how I'm going in this direction 2 times the yellow vector. And then I'm taking a right turn, not a hard right turn, but sort of a midland right turn. And then I'm moving in exactly the direction of the 4, 4. So you can see this line right here is parallel to this yellow one, because I'm moving in the 4, 4 direction, even though I didn't start in the same place the 4, 4 vector did. Remember, a vector has a direction and a magnitude, not a point of origin. So I'm moving 2 in this direction, 2 of those vectors, and then 1 of the 4, 4 vectors in this direction, I get to the point 6, 8, which is exactly what we found in domino land. Another example, what about 3, 2? That was another one that we started with. And remember, the answer to that was negative 1, 1. So what we do is we move negative 1 in the 1, 2 direction, which takes us to negative 1, negative 2. Then we turn around and almost do a complete 180, but not exactly a 180, because now we're going to move in the 4, 4 direction, 1 of those 4, 4 vectors to get up there. And it's pretty clear to see that any white point I gave you we can get to, right? I can get to 0, 4 this way. I believe the solution to that was to say, let's move 4 of these yellow arrows up here, and then scooch back 1 of the 4, 4 vectors. So you can see we don't always go in the right direction, so to speak. I mean, we kind of have to go 3 steps forward to go 2 steps back. But that nevertheless does get us to the point 0.04. Another one we did was the point 0.72. And for that one, we're going to go negative again in the 1, 2 direction 5 times. So -5 at that vector. Then turn around and go, I believe it was 3 of these 4, 4 vectors that way. And we get up here and we get to that point. You can get to any point. I remember when I first learned this, I sort of had doubts about that because I was thinking, well, both these yellow vectors, they're both kind of northeast-ish. So, I'll believe you can get to a place that's kind of over here, maybe anything in this quadrant here. But are you really able to get over here? I mean, totally perpendicular to these things, way off into this quadrant? Surely there's no way to combine these two northeast vectors to get a northwest thing. But actually there is, and you just have to zoom out a little bit. So let me kind of zoom the picture out. You'll see my yellow vector shrink here. And what we did was we shot way up here, 8 in this direction, to get all the way out here in La La Land, before we then pulled our almost 180 and zoomed back this way several vectors of the 4, 4 class in order to get here. And so this aligns perfectly well with what we noticed in the domino game, or with what you hopefully noticed, which was no matter what white domino I gave you, you were able to get there because you were able to combine the 2 yellow dominoes and get there. Provided the dominoes were yellow, right? All bets were off, and we went to the blue case, and here's what the blue case looks like. We started off with 2, 3, and 4, 6. Completely different animal, and you should see at a glance here immediately what the problem is. The problem is that these 2 vectors are pointing in the same direction. I don't mean kind of the same direction, like our 2 yellow ones were kind of northeast. I mean these 2 are exactly on top of each other. And what that means is that when I move in one of their directions, I can't get off this line, which is fine, because I have a second vector, right? I have a second domino at my disposal. But the problem is that second domino doesn't help us get off the line either. And so the combination of the 2, I can't get anywhere. So as long as I'm asking for a point on that line, which was our first case, right? I said, can you find 6, 9? There were several ways to do this. The one I showed in the video was this rather strange solution. I said, hey, I can go -3 of the shorter vector and then turn around and go, I forget how many it was, to go back up here. But I end up getting to the point 6, 9. But there's basically infinitely many different ways we could do that, right? The one you probably came up with, I'm guessing, is the more simple one of saying, well, let's just add 1 of the first vector and 1 of the second, duh. And if I add 2, 3 plus 4, 6, I get 6, 9. But there's many other solutions. I could say, hey, let's go 1.5 times the 2, 3 vector. And then let's go, what is that, 2/3 of the 4, 6 vector, or 3/2, or I forget what it is, but point is, I have the 4, 6 vector at my disposal now to go some additional yardage, and I can get up there. Let me shrink the graph a bit, and I can even shoot past it in this direction, right? What if I add 4 times the 2, 3 direction? Then I'm going to go past my point up to here, then turn around, do a UE, come back here and get to 6, 9 with some other ones. And so you can see that I can always get to any point on the line in many different ways. And that's true also of the point 0, 0, right? I can go to 0, 0 by saying, let's go up a 2, 3, and let's go back half a 4, 6. Or I could do that in many, many other ways, right? The 0, 0 is just another point on that line. So we'll come back to that in a minute, because that is one thing that's interesting about blue dominoes that's different from yellow dominoes, and that has to do with the so-called trivial solution, which we'll talk about in a minute. But notice that everything breaks down as soon as I have any other point on this plane. If I have 5, 1, forget it. There's no way you can hunt all day, and maybe you did in the blue domino segment, to combine 2, 3, and 4, 6. You're never going to get over here because you simply can't get any ammo in the northwest, southeast direction. In fact, you can't get ammo in any direction except the exact direction 2, 3, 4, 6. Even this one, which I gave you, look at that. That guy's right near the line. And yet, as I said, and I still maintain this, there is no way to get 3, 4 either from any number of 2, 3, 4, 6s because you simply can't get off the dime. You can't get off that line. All right? Now, what I'm going to introduce now is this concept called linear independence, and that's exactly what's going on here. And what I want to do is draw a connection from the dominoes to the concept and the term that we're going to be using throughout the rest of this course. All right? So here's my little cheat sheet here. I'm going to make 2 columns. One is the yellow dominoes column, and one is the blue dominoes column. And notice I have our 2 linearly independent dominoes here, and I have our two linearly dependent dominoes over there. And the first thing in this category for each one is what this notion means. Linearly independent simply means pointing in two different directions so that I can actually make use of both dominoes. The blue case, if you think about it, the problem there was that once I gave you the first domino, you could go in the 2-3 direction as much as you wanted. Okay, that was great. But then when I gave you this domino, I didn't actually give you anything that you didn't already have with the first one, right? That second domino was basically a waste. I had a student one time who did this exercise and said, that second domino is really the same domino as the first one. And he was right, it's not literally the same. But since it's a multiple of it, it might as well be the same for purposes of getting anywhere on that plane, all right? One of the key insights here is that you can't get any yellow from the other yellows, right? Now stare at that for a minute. If I give you just 1, 2, there's no way you can make 4, 4 out of the 1, 2. And conversely, there's no way you can make the 1, 2 out of the 4, 4. They are different in that regard. They're independent of each other. Neither one can be manufactured from the other. That's exactly not the case with these blues. Once I give you 2, 3, heck, you could get your own 4, 6 just by doubling it. If I give you 4, 6, you could get your own 2, 3 just by having it, right? So that's the key insight here, is that linearly independent basically means none of them can be manufactured from the others. With blue, in fact, they can be. I asked you once in the domino game segment, which of these two cases do you think is more rare? Do you think it's more common to get it where you get screwed up, or do you think it's more common where you get it so that you are all right and you can get anything in the plane? And maybe you'll see that it's actually far more common to get the yellow case. Because the blue case, the only way I can get that is to be fantastically unlucky, right? I give you the first arrow, right? First vector. Now I'm getting ready to give you the second one. Man, if you pick anything at all except one that's pointing in the same direction or the exact opposite, you'll realize if I give you one that's 180 degrees off the first one, that's also going to be trouble, right? Because that's not going to give you any more off the line power than you had before. But unless you have that fantastically improbable case, you are going to have a yellow domino thing. So the way to think of linearly independent is just that it's kind of hard to be linearly dependent, at least in what we're looking at now. Now that's going to change a little bit later, and so I'll keep you in suspense there. Next one, as we learned, you can produce every white domino with yellow dominoes. However, from blue dominoes, you can only get a very, very, very small number of them. However, it's true that with blue dominoes, every goal you can reach, you can get in a zillion different ways, whereas in the yellow domino case, it's reachable in just one way. And then the last one here, I mentioned this as we were looking at the graphs, and so let me just kind of give you this again. You can't get the 0-0 domino, or actually any domino, except in one way, right? And the only way you can get the 0-0 domino with yellows is to say, well, I'm just going to take 0 of the first domino and 0 of the second domino, right? In fact, I don't even care what my dominoes are. I'm just going to take 0 of both of them. That gives me 0. Duh. With the blue dominoes case, you can do that, of course, but you can also get it in many more ways. I can say, give me 2 of the first one and -1 of the second one. Boom, you're at the 0 vector. Give me -4 of the first one and 2 of the second one. Boom, I'm at 0, 0. I'm in double blank. So one of the factors about yellow dominoes is that you can only get that thing trivially. You can only get it with the so-called trivial solution, which is neither one of the dominoes. And that's a good way of testing for linear independence, as we'll see. So here's your definition. A set of vectors is linearly independent if you can't make any of them from the others. All right? Keep in mind that a set of vectors is what's linearly independent. If I give you a vector, it is neither blue nor yellow. There's no sense in which you can say, this is just inherently, intrinsically a blue vector. It's not the case. It's a blue vector with respect to something else. It's a blue vector when combined with something else that happens to be pointing in the same direction. But it's only the set as a whole that can be considered linearly independent or linearly dependent. For dominoes, okay, in the two-dimensional case, this basically just boils down to if one is a multiple of the other, they're dependent, otherwise they're independent. Now, unfortunately, it's not quite that simple when we go bigger. So let's think about the case where we have triominoes or quadroominoes or quintaominoes or whatever, right? Dominoes that have 100 elements in them, we can certainly have vectors that big and far, far bigger. Turns out that if one of the vectors in your set of triominoes or quadrominoes or whatever, if one of the vectors in that set is a multiple of one of the other ones, then they are linearly dependent. That is true. However, there's other ways it can be linearly dependent. So here's an example here. What if we go to the three-dimensional case, and I give you these three vectors: 2, 3, 1, 1, negative 1, 2, 7, 3, 8. Now, if I just asked you to eyeball that and tell me whether they are linearly independent, what would you say? I would certainly say they look like it to me. These look as yellow as heck, right? They look as yellow as the sun. Because neither one of them you can get from any of the other ones, right? I mean, good grief, they're all pointing in totally different directions. It's pretty random. However, not so. Consider that if I take the first one, 2 of them, and I take the second one, 3 of them, and I add those together, that linear combination does in fact add up to 7, 3, 8, right? 2 times 2 plus 1 times 3 gives you 7. 3 times 2 plus negative 1 times 3 gives you 3. And 1 times 2 plus 2 times 3 gives you 8. Okay? So simply by looking at the vectors pairwise, you cannot tell whether or not they are linearly independent when we get to more than 2. And basically the way you want to think of it is this. Once I gave you those first 2 triominoes, again, you didn't gain anything by the third one, right? Because the third one you could have made yourself. You could have made that third triomino from the first 2. Therefore, that tells you something. That tells you that there's a rat, right? Tells you that I've pulled a fast one on you and I've smuggled something in that's not quite legit because I gave you a vector you could have already gotten. The only way you can have a full independent set of vectors is if each one that I give you is a brand new Christmas present to open that is nothing that you could have made before. That's the only way that vectors can be linearly independent.